graphing logs. So here's what I want you to do in your calculator. We're going to be choosing a base to use for our log. What base would you guys like to use? Anything between like 0 and 4. Between 2 and 4, I mean. 2. Okay, let's do log base 2. So we're going to graph y equals log base 2 of x. So in our graphing calculator, we're going to hit y equals. And then how do we type log base 2? Math, up, log base 2 of x. And then we're going to hit the graph button so we can see what the graph looks like. There it is. Does this remind you of another graph that you've seen before?
Yes.
Yes? What does it remind you of?
I forget what it's called. Exponential.
Should remind you of exponential. There's another graph it might remind you of. Probably not. Well, quadratic is U-shaped. Yeah, it should remind you of a square root graph. Because I'll show you, you don't have to graph it on yours, but a square root graph looks like that. So really similar. Square root graph is just slightly different. The big difference, and actually maybe let me show you, I'm going to show you on Desmos instead because it'll be more clear. So, yes.
I don't have the log thing.
You don't have what?
Like when I do like math, it goes through. I don't know what that is, but it's not the log base.
If you hit alpha y equals, does it give you this? No? Your calculator's just not updated. You just need to grab a different calculator. Okay, so I want to show you guys the difference so you guys can really see. So I need everybody to look up here. Here's a log graph, and here's a square root x graph. So what's the big difference? Yeah, the square root graph like ends at 0. Everyone see that? Or starts at 0. It stops right there. Does the log graph end at 0? No, it keeps going. Everyone see that? Like it's going down here. The square root graph is long gone. It is not, there's no more points there. The log graph has actually continued all these points down here. It has continued all the way down there. We can still see red. It is continuing. Anyone remember what that's called if you still have points? You're getting closer and closer to that line. If there's still points there, it's not stopping. Yeah, there's a dotted line. There's an asymptote there. So square root graphs, they stop suddenly. Log graphs don't. They have asymptotes. That is the big difference. To the naked eye, they look the same if you were to graph them on a graphing calculator, but when you graph them on Desmos, you can tell they're definitely different. So that's one thing where you have to be smarter than the technology that you're using. So if you're using a graphing calculator, you have to recognize that the square root graph does stop. The log graph does not stop. So we're going to write that on our notes just to keep in mind that these two are different. So we're going to write a little note right here to ourselves. Y equals square root x looks like this. It's got a point, and then it goes up like this. That's a square root graph. Y equals log base b of x. It doesn't matter what your base is. It looks like this. Arrow going down, arrow going up. This is typically how students incorrectly draw a square root graph. Students love to put an arrow at the bottom of a square root graph, and that's wrong. They're actually drawing a log graph, and they don't even realize it. So log graphs, they have an asymptote right here. They actually go almost perfectly vertical right here. Your calculator has a hard time graphing that. So if you take a log graph and you shift it up a certain amount, you'll actually make the log graph look like it has stopped. So if I take this log graph and put like +5 on it and graph it, it makes it look like the log graph stopped, and it didn't stop. It's just that our graphing calculators have a hard time graphing things that look like vertical lines. Does that make sense? Because our graphing calculator only graphs functions, and functions don't have vertical lines in them. So it's not that logs are not functions, they are. It's just that log graphs are particularly difficult for TI-84 calculators to graph. Does that make sense? Desmos are really good for these graphs, the graphing calculators not so much. So we have to be a little bit smarter. We have to understand how these graphs work when we use the calculators. All right, so what we're going to do is we're going to go into the table. We're going to get some points from this. So y equals log base 2 of x. I'm going to hit second graph. I'm going to look here and get some points. So if you were to plug in 0, you get an error message. That is your vertical asymptote. So we're going to draw that in as a dotted line. And the reason you get a vertical asymptote there is because you cannot plug 0 into a logarithm. So I'm going to say vertical asymptote at x equals 0. And then you'll actually notice, just like if you looked at the graph, there was nothing on the left side. You can't plug any negatives into a logarithm either. No negatives, and you can't plug in 0. So 0 is where the asymptote was. The asymptote acts like a fence. Nothing can happen to the left of the fence. And if we look back at Desmos, you can see that's true. So there's your vertical asymptote acting like a fence. Nothing gets past it. All right? So when we look at the table, we can definitely see that's true. 0, here's our fence, and then to the left of our fence, nothing happens. Okay, the next point we have is the point 1, 0. So over 1, 0. And then the next point we have is 2, 1. 2, 1. Now, the reason it's 2, 1 is because 2 is the base. So the 2 points we're going to see on here is we're going to see 1, 0. That's going to be true for every logarithmic graph. And then the next point is going to be the base, comma, 1. So we're always going to have, for a parent graph that has no transformations yet, we're always going to have an asymptote of 0. We're going to have the point 1, 0, and we're going to have the point base, comma, 1. And then once transformations start happening to the graph, these points are going to move around. There is no such thing as a vertex or a locator point with a logarithmic graph. So when we look for graphing the logarithms, we're going to start with wherever the vertical asymptote is, and then we're going to look to see where the points are that are slightly to the right of that. So I'm always going to look for that error message to see where my vertical asymptote is first, okay? And you can always see that based on what would be 0 plugged into the log. How could you plug 0 into the log? That's where the vertical asymptote is, okay? So if you look at how this is graphed, we're always going to draw the points so that they come along and get closer to the vertical asymptote, but don't touch it. That's how we always graph these. All right, so if we draw the points, we're going to start with the one that's further away, and we can just draw it closer here and then follow along the asymptote. We know it goes down forever. And then if we look at the picture, this one goes out and it gets pretty level very quick. So it doesn't go up very fast at all. So it levels out kind of like this. Okay. So if we use that same idea over here, we know that this is y equals log base e of x. So this graph is going to have a vertical asymptote at x equals 0 also. This graph is also going to have the point 1, 0. And this graph has a different base. It has a base of e. And does anyone know what the decimal for e is? Yeah, 2 point. We can check it. 2.71. Yeah, so there's an E button right here on your calculator. It's in blue. So if I get out of this, I can hit second this button, and then that'll get me just a plain E. Or the other place to do the E is above the ln button. This allows you to do E to any exponent, because we typically want E to an exponent. And if I just want a regular E, then I would want E to the first power. So 2.718, and I'll just do 2.7 because that'll be easiest for me to graph. So I'm going to get the 0.10 and then the 0.2.7, 1. So over 2.7 up 1. Okay, and I'm going to do the same thing again. Okay. So the transformations for these graphs are going to be the same that you guys saw in Math 3, the same that we have looked at in the couple graphs we've looked at this year. So the A value tells you if the graph has a vertical stretch or a vertical compression. So the graph is vertically stretched if the A value is greater than 1. It's vertically compressed if the A value is less than 1. It doesn't matter what sign it is. Doesn't matter if it's positive or negative. Just if it's greater than 1 or less than 1. If the A value is negative, then you have a reflection over the x-axis. And the A value is the same for both of them, whether it's log base B or if it's ln, which we know is log base E. The C, I put a C value. Normally I put a B value, but these graphs have a base of B, so I didn't want to use the same letter twice. So the C value is the horizontal stretch and the horizontal compression. And remember, these are just backwards of what we typically would think. So if the C value is less than 1, it's a horizontal stretch. If the C value is greater than 1, it's a horizontal compression. And if C is negative, it's a reflection over the y-axis. The H value tells you if the graph moved to the left or the right. Again, kind of the opposite of what you would think. A positive moves the graph to the left, a negative moves the graph to the right. The K value will tell you if the graph has moved up or down. This is exactly what you would think. A plus moves the graph up, a minus moves the graph down. The B value is not considered to be a transformation. It is just the base of the graph, so it tells you which parent graph you're looking at. So you can address it when they ask you what the transformations are, but it's not technically a transformation. And then make sure that whenever you see the inside of the function, you always factor the inside, because this is the inside in factored form. And sometimes they'll give you the inside in factored form, but oftentimes they won't. And if you try to describe the transformations of the inside not in factored form, then your left and your right shift will always be incorrect, and you'll get one of your transformations wrong. Okay, so if we look at example 1, I can see 1, 2, 3, 4 transformations. Before I say what they are, I need to rewrite this equation. So how do I need to rewrite it? Perfect. So the inside needed to be factored. Okay. So what are the transformations? Okay. Reflect over x. Horizontal compression. And you said left 1, up 1, okay? And then what is the vertical asymptote? You're close. It has to be whatever would make this equal 0. -1. So vertical asymptote x equals -1. And remember, your vertical asymptote is a vertical line. It's the equation of a vertical line. So it has to be whatever I could type into Desmos that would actually graph. If I were to type -1 into Desmos, that wouldn't graph anything. Desmos would be like, yeah, I'm ready to be a calculator. To get it to graph in Desmos, you have to actually give it an equation. X equals -1, that's an equation of a vertical line. Once I type that in, it would actually graph it for me. So, and you can see if we could put the dotted line right here. X equals -1, there's your dotted line for your vertical asymptote. Okay. So an asymptote, back in the day when you very first learned it, teachers typically give you an oversimplified example of what an asymptote is. They typically say it's an imaginary line on the graph that you can't cross. That is incorrect. Doesn't mean your teachers are bad teachers. It's just the easiest way to explain an asymptote to students who are going to have a very hard time understanding the real definition. So once you get into classes like honors or AP pre-calc, or you get into calculus, you start to realize that asymptotes can be crossed. More complicated graphs do cross asymptotes. These asymptotes will not be crossed. So the definition that you might have learned by teachers back in the day, where you learned that an asymptote is an imaginary line that cannot be crossed, that is still true for this particular unit. But the actual definition of an asymptote is that it's an imaginary line where the distance between the curve and the line is getting closer to 0. That's what the actual definition of an asymptote is. So you could cross over the line as long as the distance between the curve and the line is getting smaller and smaller. So typically we graph asymptotes with dotted lines to show they're imaginary, they're not actually there, they're not actually part of the graph, but something is certainly happening there, and it's happening with like a line that's not actually showing up. All right, next thing we're going to be finding is domain and range. Just a reminder, domain has to do with x values, range has to do with y values. So we're going to keep remembering that. So if we look at this next problem, now look at this picture. This graph had been shifted up 4, and based on the limitation of the technology, it's getting closer and closer to that vertical asymptote. And then the graphing technology had a hard time graphing any further than this, because it was graphing something that was basically straight up and down, and the graphing technology stopped. Couldn't graph anymore because it was getting too vertical. Did the graph actually stop right here? No, it did not. So we're going to add an arrow there because we know the graph did not stop. Even though the graphing technology had a hard time, we know that graph keeps going. Okay, so let's find the vertical asymptote first, because that's definitely going to influence one of our answers for the domain or the range. It's going to influence something. Can anyone see what the vertical asymptote should be? Should be 3. So definitely not 6. We have to think about what this would be if we factored it. So it would be 2 times x minus 3. And that means that the vertical asymptote is x equals 3. Okay, domain is x values, range is y values. So if we look at this graph, we have an asymptote at 3, which for our purposes is going to act like a fence at 3. We're going to have a fence that we basically can't cross. So what would the domain be? How far to the left can the graph go? How far to the right can the graph go? 3 to the left, and then how far to the right? Infinity. Now, for the 3 to the left, does the graph actually touch 3? It does not touch 3, so what do I put here? Parenthesis, okay, and then does the graph touch infinity? No, so we put another parenthesis. Okay, for the range, how far down, how far up does the graph go? Yeah, down forever, up forever. Okay, increasing and decreasing interval, these are always both x values. So you're describing where, which is x values, where the graph slants up, where the graph slants down. So here we have this graph. You can see an example of one that has not only been reflected over the x-axis, but it also has been reflected over the y-axis, and that makes it kind of look like an exponential function. It's been reflected both ways. So if we look at this graph, I'm going to put, I showed you guys how I do the stick figure, right? Stick figure walking uphill, stick figure walking downhill. So if we do our little stick figure, which way is our stick figure walking? Uphill or downhill? Uphill. Okay, so which answer are we not going to have anything for? Decreasing. So I'm going to say none. Okay. Now, this is still a log graph, which means there is still a vertical asymptote somewhere in this graph. So where does this graph stop? And we don't have any numbers past that. 0. So if this is the inside of the function, we have to think about where the inside of the function would equal 0, and negative x would equal 0 at 0. So there is a vertical asymptote right here. Okay. There's a vertical asymptote right here, because these graphs, if it says the word log, it always has a vertical asymptote. So this graph stops at 0 because it has just a plain x in it. It's a negative x, but it's a plain x. So if it was x, it would still be 0. Negative x is still 0. If it said x plus 1, then the vertical asymptote would be at negative 1. If it said x minus 2, the asymptote would be at 2. Okay. So now we have to write which x value it started increasing at, and then which x value it ended increasing at. All right, so what x value do we have over here for a left arrow? Negative infinity. Now over here we do have a right arrow, but that right arrow cannot get past the fence. So what number is the fence at? 0. Okay, so what is our increasing interval? Negative infinity to 0. All right, and then should we do brackets or parentheses for these? Parentheses. We can't ever actually get to an infinity, and we can't actually get to 0 because 0 is an asymptote, so we can't touch that number. Okay. Maximums and minimums, they look like mountaintops and valleys, and so logarithmic graphs don't have mountaintops or valleys. They would have, you get to get more specific on things in pre-calc where you can talk about absolute maximums and absolute minimums, but the way that these graphs are drawn, there's not even going to be those. So there's no maximums or minimums if they ask about that. So no high points and low points to the graph. X-intercepts and Y-intercepts, these are ones that tend to be tricky, in particular the X-intercepts. And one of the reasons these are kind of tricky is because logarithmic graphs are very slow growing, which means sometimes they take forever to cross the x-axis, and so you think they're just never going to. Or the other way they could be tricky is in a situation like this, where you might think the graph has stopped. Like if the graph was high enough, you might think it had stopped and that it wouldn't cross the x-axis, when in reality it actually does. So we're going to practice a couple of these because I want to show you guys how we could actually find those x-intercepts. So let's go ahead and graph this one. 2 ln x plus 5 minus 6, and then I'm going to have us graph another one. So 2... and we're going to use the ln button, x plus 5 minus 6. The ln button is under the log button. It's kind of next to the 4, between the 4 and the 7. Off to the side, the left side. All right, everybody getting it graphed? Looks like this. And the x-intercept is going to be over here on the right side. So we need more numbers in our window, which means we're going to hit window. And then we need more numbers to the right. So to get more numbers to the right, we're going to need more numbers on the x max. And what do you guys want to change it to? 25. Okay, so changing it to 25 made it big enough to find x-intercepts. And then do you guys remember how we find the x-intercepts? Second trace number 2. So x-intercepts, we do second trace number 2. So x-intercepts are called the zeros of the graph. We do second trace number 2. And then we tell the graph where to look for the answers. I know the answer is somewhere between 0 and 25. So I'm just going to tell the calculator to look between 0 and 25. So I'm going to, when it says left bound, I'm going to type 0 and press enter. And then I'm going to type 25 and press enter. And then when it says guess, I'm going to ignore the guess and press enter one more time. So go ahead and do that. Left bound 0, right bound 25, and then press enter one more time. And I'm getting a decimal. What decimal are you guys getting? So 0.86. Is that what you guys got? Yeah?
Yes.
Yes? Yes. So I did second trace, option number 2. And when it said left bound, I typed 0 and press enter. And then for right bound, I pressed 25 and pressed enter. And when it said guess, I ignored the guess and I just pressed enter one more time. And then it told me the answer. Okay? Y-intercept is a little bit easier. How do we find the y-intercept? So we can hit second trace number 1. Okay, second trace number 1, Press enter. And then what number do we want to plug in for x to find a y-intercept? We want to plug in 0. And that gives us the point 0, negative 2.781. Okay, I want to show you problems that always confuse students, where students think there's no x-intercept, but there is. So now we're going to go ahead and put our calculator window back to normal. So hit the window button. Take the 25, put it back to 10. And what we're going to do is we're going to graph example 2. So we're going to do 1/2 ln 2x minus 6, and let's do plus 4. I wonder if that'll be high enough. Yeah. What part?
I tried doing the left bound and right bound thing, and it kept saying invalid, so I gave it to my reader, and then there's a bunch of numbers on here.
I would just clear the calculator. So all I'm doing is I'm typing in example 2. And the calculator is having a particularly difficult time graphing example 2. Everyone's calculator look like this? Okay. Now, we know what log graphs look like, so we know that this isn't what the graph should look like, right? Everyone know that? Okay. So I know that this graph really should go down, and I know that the asymptote's at 3. The asymptote's right in here. I know the graph should be going down, and it should be crossing somewhere near 3. So one thing that you can do just so that you can see more of the graph is you can change the window to zoom in, and sometimes that helps. So if I change the window, instead of to be as zoomed out as 10, I can change it to something like maybe 5 could be helpful. So -5 to 5. I'm going to leave the x scale as 1. That just says that my little divots, my little notches, are going to be by 1s. 1, 2, 3, 4, 5. And then change my y scale, my y min and max to 5s. Sometimes that'll help because it'll like zoom me in. And then I can see a little bit more of the graph. You guys can see that this part is showing a little bit more now. It's off to the side, but it seems to show a little bit more of that curvature. But I know that my x-intercept is going to be really close to 3. Does that make sense? My x-intercept is going to be really close to 3. How do I know that the x-intercept is going to be close to 3? Because it has the vertical asymptote. And if I look at this, it follows along this, and then it crosses the x-axis really close to that vertical asymptote. Does that make sense? So if I look for the vertical asymptote between like 3 and 4, I should be able to find it. Does that make sense? If I look for the vertical asymptote between 3 and 4, I should be able to find it. Typically, that works for students to be able to do something like that, to look between 3 and 4. So if I did second trace option number 2 to find the x-intercept, and for left bound and right bound, I typed 3 for left bound and 4 for right bound, it typically finds it for me. So even though I couldn't see the answer on the screen, even though it looked like the graph wasn't graphing the answer on the screen, the calculator still knew that the answer was there. Does that make sense? So the calculator can still calculate it. This right here is your calculator writing 0 in scientific notation. It's just having a hard time actually getting to 0. So this is 1.453 times 10 to the negative 10 power. There are 10 zeros in front of 1.4. So this, we would have to move it back and put 0.00000 10 times. Okay, so this is scientific notation, very, very close to 0. And then the x-intercept is very, very close to 3. You've got 10th, 100th, 1000th, 10,000th. You've got the 10,000th place of accuracy there. It's very, very close to 3 because that vertical asymptote. You're kind of far off the vertical asymptote there. Okay, so you can find it even if that graph has been shifted up. Shifted vertically, it's still there. Okay, let's turn to the next page. So continuity, just a reminder, graphs are continuous if you can trace the graph with your finger without picking up your finger. So these graphs are always continuous because I can trace the whole thing without picking up my finger. End behavior is just describing the arrows. So we say as x goes to negative infinity, so this is us describing the left arrow. As x goes to positive infinity. So x doesn't go left forever because it doesn't get past the fence. Does that make sense? So for this particular graph, if we're describing this one, we wouldn't be able to say x goes left forever because it doesn't, it stops at 0. So when we are trying to say we're looking at the left forever portion, we would say y is undefined because we never got past looking at 0. We never even got to look at -1. We didn't get that far. Now, when we look to the right, what do you guys notice about the right side? It goes up. So for this one, we're going to say, as I look at the right side goes up. So I'm going to say y goes to positive infinity. Okay, so let's try graphing a couple of these just to make sure we're confident with this. So I'm going to find the transformations. I'm going to find the vertical asymptote. What do I need to do before I find the transformations? I need to factor the inside of the function to make sure I'm going to get it right. So I've got y equals negative log base 2, and then what is the inside of the function? X plus 1, okay. And then on the outside we got plus 5. Okay, so what are the transformations? Okay. Okay. Okay, the vertical asymptote is -1. All right, so I'm going to grab my calculator, and you can either put your calculator preferences back to where they were, or you can do second plus 7, 1, 2, and just clear the memory and get them back to normal. And then we're going to go ahead and go to y equals and start plugging this function in. So what should I do to plug it in? How do I plug this in? So I got negative, math up, log base 2, and I would type in the original because it's easier without having extra parentheses, so I would just do 2x plus 2, and then plus 5. Graph that. Math up, up. All right, and I'm going to look at my table, and in the table I'm going to look for -1 because that's where the asymptote is. And then right past the asymptote is where I'm going to get my points that are easy to graph. So 0, 4, 1, 3. 0, 4, 1, 3. And you can only graph 2 points, or if you see some more that are easy to graph, you could go for those. So like 3, 2 is kind of like a bonus point. I saw that one as well, and that one looks easy to graph. Oh yeah, 7, 1. Okay. How far to the left and the right does this graph go? So the left is -1, to the right is how far, did you say? Infinity, okay. Parentheses. How far up and down? Okay. Forever, forever, okay. Increasing, decreasing. If we put a stick figure over here, he's going downhill, so I'm going to put none for increasing. And then what numbers should I use for decreasing? -1 to infinity. What should I put around those numbers? Parentheses. Okay. Is there a max or a min? Yeah, no mountaintop, no valley. All right, x-intercept, y-intercept. We're going to have to find those. Oh, 0, 4. Yeah, we graphed that already. Okay, the x-intercept we cannot see on the screen currently, so how can we fix that? Window, and we need more numbers over here. So how do we get more numbers over here? In the x, max or min? Max. What number do you guys want to put? 30? No, that's fine. Okay, and then how do I find the x-intercept? Second trace, number 2. Yeah, I'll just do 0 to 30. I know the answer is in there somewhere. Oh, 15, right in the middle. Okay, domain, range, increasing, decreasing, max, min. Is the graph continuous? Yes, you can trace the whole thing with your finger and not have to pick up your finger, so yes. Now, the left arrow tried to go left forever, but was it able to get past -1? No. So we're going to say it could not get past -1, so y is undefined. What does the right arrow do? Positive infinity or negative? Negative, it's going down. Okay. Let's look at the next one. So we're going to have to rewrite this because of the inside. What should the inside look like? Mm-hmm. Okay. So what are the transformations? Up 4, left 3. Vertical stretch. Reflect over Y. Okay. The vertical asymptote is x equals -3. Mm-hmm. So 2, math, up. So it looks kind of weird this time because it's been reflected over the y-axis, so it's on like the wrong side, it feels like. So I typed it in. In the table, I'm going to look for -3 because that's going to tell me where to start getting my points. So there's the asymptote. -4, -4, -5, -5. -7, -6. Can't graph the next one. Did you put the negative x minus 3? Plus 4? Oh, I got positive y values too. Sorry guys, I graphed it wrong. -4, 4, -5, 5, -7, 6. Yeah. Okay, looks like that. All right, everyone got that one? Yes? Okay. One thing I noticed about the assignment is that I also asked you to find the base, so let's do that for these two. So what's the base for example 5? For example 5? Base is 2.
You can't see that in the graph, can you?
You can't see it in the graph, no. You could maybe find it if you're like real talented, but honestly, I wouldn't be able to find it. That'd be hard for me. What's the base for example 6? Base is 4. Okay. All right. I think we can probably find the other stuff, so I'd rather let you guys get started on the assignment. So I'm going to go ahead and pass it out.